So in this video I will make a small update in the project about detecting the gastro reflux using impedance and pH. The last time I implemented the model for predicting the presence of the absence of an event in a timestamp wise manner. So I have a binary prediction for each timestamp. I evaluate the model. I have some metrics. It wasn't that bad, but also it wasn't that good. In particularly because it's really hard to tune the threshold for determining when there is a presence of the absence of an event, and then the thing of merging consecutive regions of true events. But I will create a video later comparing the two models and the results, and probably also for explaining all the work done for relabeling the whole data set, which wasn't easy at all but needed. But since we faced the thing of a model that wasn't predicting an event but just a timestamp, I implemented this kind of YOLO model in which we predict the event. So the start at the end, or the center and width of the event. So as usual, we are trying to predict this kind of events in which there is a drop of at least 50% in the channel more close to the stomach, and then a progressive going upward in the drop in the following channels closest to the mouth. It can arrive not to the top one, but at least it should be in the first and probably the second one, at least, for being taken as an event. And there are a few normal patterns, one with liquid, one with mixed content in the esophagus, in which we have these huge peaks, a huge drop, and then a peak, and then in the presence of gas, and when the impedance goes really high. This is the clear event to detect. It's not that easy in the real data set, but this is what we are looking for. So we need a fast and reliable model. We have a data set of around 100 patients, labeled and relabeled. We are finishing to relabel everything, and then the model should be able to run in CPU offline in the doctor's computer without anything else. So it should be fast. We cannot expect that the doctor have an amazing computer to run the model. So instead of predicting one prediction per timestamp, was missing 30% of probability, 100 probability, 130%. For each timestamp, we are predicting the center and the width of the event. So we have a contiguous region in which we say, okay, the event starts here, and the event ends here. So what thing do we need? Since we are using kind of a YOLO model, we need some definition of what they call anchors. We need to prepare the data set using into consideration these anchors, creating a model capable of predicting what we want, training the model, and then we are going to list the two steps that they are missing right now. So the idea is, okay, we have the input equal to the U-time model. So we have the timestamp divided in overlapping or possibly overlapping sliding window. But instead of having prediction for each timestamp, we propose, as YOLO does, a set of anchors. So in which each event must be mapped. So for example, we have four kind of anchors at the beginning, one really small, medium, a bit larger, and super large. At the middle the same, at the end the same. In the image model of YOLO, the image is divided in subcells of the image, and each cell proposes a set of anchors, with the idea that you can have objects in different parts of the image. Since we are dealing with a simpler thing, we are expecting at least two, maximum three events in the same window, and we can just reduce the complete window to a subset of 4 times 3 or 5 times 3 anchors in total. Well, we propose these anchors, and then we have to match each true event, which is drawn in green, to the closest one, or the one that maximizes intersection over union. So in this case, this true event will be mapped to this anchor. So for our data set, we will predict not the position and the width, but how I must change this anchor in order to arrive to this event. So basically the displacement I have to do a little bit to the right apparently, and the difference in width a little bit wider, in order to be able to capture this event. And of course also the confidence. So the idea is to this anchor assign a value of 1, indicating that there is event here, and the other anchor should be 0 basically. So what we do in the dataset preparation phase, for each of the events that enters in the sliding window, or even if the event is not completely inside, is overlapping with the percentage inside the time series window, for each of the events we match with an anchor computing the intersection over union, and we have a set of use anchors. So the anchor in our case is just assigned to one single event, and then we use the candidate with the maximum intersection over union as the anchor selected for this particular event. Once we have the particular event that maximizes intersection over union with the true event, we compute the relative displacement, and we compute the logarithm of the ratio between the anchor and the event. So we are predicting just the displacement of the center relative to the anchor, and the logarithm of this, how much do we have to scale the anchor in order to obtain the true event. So we have at the end 2 linear layers for the prediction of our event in the model. So what we have at the end is a data set with, in our case, I think in the model we have 5 anchors divided in 5 anchors per beginning, middle, and end. So we have 15 anchors. The first position will be the relative shift. I have to move the anchor. How much do we have? The logarithm of how much do we have to scale in order to arrive to the event from the anchor, and 1. So at the end, this is our thing that we have to regress in our model, and the other ones will be 0. So since we have to predict 3 values for each anchor, we have our backbone, whatever it may be. In this case, we are using just convolutional layer for the feature extraction, and 2 attention layers, and then a final head. We predict 2 values for the displacement of the center and the scaling, with the linear layer at the end, and just the sigmoid for the confidence. And then we concatenate everything, and this is what we are going to output as our output value in the network. Then we have the loss function. It's the other thing that we need. So since we are using a simplified version of YOLO for 1D, we are using a similar loss at the end, in which we combine the position loss and the prediction loss. Basically, we are using the intersection over union, but also penalizing the displacement and the aspect ratio. So it's not just the intersection over union between the predicted and the true, but also how far they are and how dissimilar they are, basically. And then we are using the binary cross entropy for the true and for the negatives, but computing the mean just for the positive and computing the mean just for the negative with a weight for the non-object, as YOLO does. So basically this is the coordinate part, true positive, the true events part, and the non-events part weighted. Our measurement of how well our events match with the predicted event. We are measuring, I think it's complete intersection with union on the C. We are measuring the intersection over union between the predicted and the true, also penalizing how far they are and how dissimilar they are in terms of the aspect ratio, so basically in terms of the width that they have. So in this case we are trying to doing the center as close as possible, the width as close as possible, and of course this will maximize also the intersection over union, so we are trying to being as good as possible in every possible sense. For trying to evaluate the training procedure, we are implementing a few metrics, classic metrics, intersection over union during training, the precision and recall, to try to see how well we are matching these events. So of course we have really few events with respect to the complete set of studies, so it's probably needed to tune the threshold to have a proper detection rate, and not being so under predict or over predict a lot. But this will be part of the evaluation, also comparing to the around 60% that has the per timestamp model that we will come later. Okay, the training is working, at least. It's a bit overfitting at the end, but at least the losses are similar, they are going down. So I think it's working. I saw the plots, the events are being detected. Okay, that's not bad. The next step will be adding a non-maximum suppression in case we detected multiple events overlap. So we will have to choose one of them, and then make a proper evaluation of the model. So we have some metrics in order to be able to compare with the U-time model per timestamp. Once we have this information, we will need to export the model in order to use it in the software, but this will be later. And for now, this is it. And then in the future, I don't know when, but probably in a few days, weeks, I will try to create another video with the tour of the project and also the issues that we have with the dataset, the labeling status of the dataset originally, and what did I do in order to have a correct label dataset by basically asking people to relabel, asking doctors to relabel all of these studies. So it was a complicated thing.